Complex analysis, when compared to real analysis, for example, is quite different in nature in many ways. Much richer, you can say, okay, and much different in flavor. Although we're going to still talk about differentiability, integration, and so on. But the flavor is quite different, and there is some remarkable things which go on in the complex domain, as you will see, compared to the real domain. The Trimurtis of the subject of complex analysis, or the three names that you see on the board: Cauchy, Riemann, and Weierstrass. Although, of course, complex numbers and analysis with them and so on were there earlier, at least from the time of Euler, Lagrange, and so on. In fact, Lagrange has a book called Theory of Analytic Functions. But the real beginning of complex analysis, you can say, started with Cauchy. Cauchy is the three people there. Their approaches are quite different. Their, so to say, the philosophy are quite different. Cauchy, the central thing for Cauchy was the integral of a complex valued function on a domain in a complex plane. Integral along a curve, that's the basic thing for complex analysis these days. Riemann's main underlying point of view is geometric. See, the thing you see here at Riemann, this was the thesis of Riemann, a doctoral thesis. So that was where, for example, you find Cauchy-Riemann equation. Of course, Cauchy-Riemann equations already were studied by Cauchy himself. So Riemann's point of view was geometric. So, for example, mapping properties of analytic functions, conformal mappings, and then what are called Riemann surfaces. They were all introduced in this thesis of Riemann. For Weierstrass, the basic objects are power series. So everything was developed from power series by Weierstrass. Of course, it turned out that all the approaches, different approaches, were essentially equivalent. So Weierstrass, I have not written any reference as such, because basically most of the results of Weierstrass were through his lectures. Okay, not published papers generally. All of them were published later as collected works of Weierstrass, but the main credit for the availability of this work of Weierstrass go to his students who meticulously took down notes, Killing and many others. I think the major notes taker was Killing. I don't know, you might not have heard of Killing. If you have studied some Lie groups, Lie algebras, you might come across the word Killing. There is something called the Killing form. So thanks to Weierstrass students, all the lectures of Weierstrass have been recorded. So these are all later published collected works of Weierstrass. So Weierstrass was for a very long time a school teacher. Only much later in his life he became a professor at Berlin, and his lectures were attended by almost all the well-known mathematicians of that time. See, these days people talk of the Weierstrassian rigor in mathematics. So the rigor, the modern day, probably you don't realize. See, earlier mathematics was not like the mathematics that we study now. Okay, definition, theorem, proof, and all that. Okay, so people were much more loose, you can say, right? There was not much of a rigorous treatment of topics of convergence or continuity or even notion of a function and so on. Okay, so the two most important proponents of this mathematical rigor were Dedekind and Weierstrass. So, for example, the epsilon delta definition of continuity or limit is usually ascribed to Weierstrass, although actually there is Bolzano several decades earlier had actually given this. Bolzano's work came to light only much later. So anyway, let's not go into that. Okay, so of course Cauchy was one of the most prolific mathematicians of all times. You understand what it means? Prolific means his output was so much. Okay, and he published papers in almost all subjects in mathematics. You might have come across Cauchy's name in many different places. Okay, group theory, real analysis, complex analysis, elasticity, this, that, whatever. I don't want to get into too much of these stories. Okay, Riemann, of course, was what you call as a seminal mathematician. He published very little, very few papers, but whatever he published started a new branch of mathematics, so to say. For example, the most well-known of Riemann's publications are just you can count in your one hand, I suppose, fingers one hand. This was his dissertation, PhD dissertation, and then his what is called the habilitation shrift was on Fourier series or trigonometric series, where, for example, the concept of Riemann integral was introduced, and then what is called his habilitation lecture was on differential geometry that I mentioned probably in the last course on differential geometry. And there was a later paper on the Riemann zeta function, which became the starting point of what is called the analytic number theory. The zeta function actually was already there. In fact, Euler had studied it, and there is something called the Euler product for the zeta function. The essential difference was that Euler considered only the real variable. The genius of Riemann was that he introduced the complex variable there, and that made all the difference. So let us get into something, okay? Except for occasional remarks now and then, I will not go into much more history of the subject. So for our purposes, the most important work of Cauchy was the 1825 one. This was a much longer thing. This more or less a summary of important things from here. This was 1914, but it was published only much later. So most of our basic things that we need appeared in this 1825 memoir of Cauchy. So the basic property that we are going to start with is differentiation. Okay. So when you look at differentiation, for example, on the real line or an interval on the real line, you have the usual definition, right? Limit of something f of x plus h minus f of x over h at h tends to 0, this and so on. Same definition, of course, you can carry over to the complex domain. But unlike the real case, some magic happens in the complex domain. So if you're looking at functions of a real variable, so when you say the function is differentiable, okay, it is differentiable, okay, but you don't get any freebies, so to say. If you buy one, you get one free. Nothing of that kind you get on the real line. But in the complex domain, the situation is dramatically different. If you buy one, you have infinitely many freebies, so to say. So going back to the real case, if you assume that function is differentiable once, that's it. You don't get anything more, right? A function which is differentiable once need not be differentiable once more. Of course, you can easily construct functions, right? You know how to, examples of functions which are continuous, not differentiable, right? If you start with such function, you can keep integrating. If you integrate such a function, you will get a differentiable function. So that is not twice differentiable, and so on. You can keep repeating it any number of times, so that you can get functions which are, say, n times differentiable for any n, but not n plus 1 times differentiable. But the situation is dramatically different in the complex case. If you assume a function is differentiable in a domain once, you're going to end up with infinite differentiability. First objectives of this lecture, let us say. One of the first things that we try to get. But there is much more than that, actually. You actually get power series expansion, local power series expansion. That is, if you have a domain in the complex plane, we'll come out of all this more detail. So if you have a function which is differentiable in a domain in the complex plane, take any point in the domain. Around that point, there is a disk in which you can expand the function in terms of a power series. You know what a power series is, right? We'll be talking about them anyway. And power series, functions which have power series expansions are much more than infinitely differentiable in the real case. Of course, in the complex case, as I said, even if you assume once differentiability, you are going to end up with power series expansion. So, analyticity is usually expressed in terms of power series expansion. You can also talk about real analytic functions. There, what you mean is the function has a power series expansion. But the way we are going to define complex analytic functions is through differentiability. But as we will see as we go on, this in turn gives you the power series expansion. So people sometimes make a distinction between analyticity, which means power series expansion, and what is called holomorphic functions in the complex domain. Of course, as it turned out, both are equivalent. All right? That's what we will see. So going back to the real domain again, so even if you assume a function is infinitely differentiable, it may not have a power series representation in the real case, right? A function may be infinitely differentiable on an interval, for example, but it may not have any power series expansion around any point in the interval. A power series expansion is something like that, okay? or more generally, power series expansion around any point. It need not be about 0. This is what is called a power series. Of course, when you are in complex domain, put z instead of x. That's all. So we'll look at this. In fact, power series expansion. Power series give you, even to start with. See our approach. The modern approach is a mixture of all these Cauchy-Riemann and Weier. Okay, but we start with Cauchy's definition essentially, although with a slight modification. But so end up with Weierstrass definition. So I can quickly give an example in the real case of a function which is infinitely differentiable, but does not have a power series expansion. Right? This is a standard example you have. So you look at, for example, look at fx. At least to start with, you can see that it is continuous. I mean, only problem, if at all there is a problem, will be at 0. So everything you check at 0, that everything is fine. So everything is going to be fine everywhere. I mean, the basic thing that you need in working out this example is that the exponential function grows exponentially. I mean, that's where this term comes from. Because e power x goes to infinity very fast compared to, say, any polynomial, for example. I mean, that's how the term exponential growth has come into even the language, not only mathematics. So that's the basic thing that you will need in verifying this example. So if you look at x power n into e power minus 1 by x, as x goes to infinity, this will go to 0 for any n. That's the thing that you will need when you differentiate and so on. So you can check that this function has derivatives of all orders, and all the derivatives, I'm going to look at only the point 0. Other points there is no problem. On the negative side it is 0. On the positive side you differentiate this function. Okay. All the derivatives at 0 are 0. But if the function has a power series expansion, so let's say, suppose fx like this, convergent power series expansion in some interval around 0, let's say, for example. What are the ANs? So this we will see in the complex case also, right? So ANs are given by the derivatives, the coefficients in the power series. The nth derivative at that point divided by the factorial n. But if all the derivatives are 0, all the ANs are 0, and also the power series reduces to 0. So it can't represent the function that we started with. Okay? So this function has no power series representation around 0, although it is infinitely differentiable. So one of the first objectives here for us would be to show that such a situation does not arise in the complex case. So in the real case, you will say, for example, this function is infinitely differentiable function. It is not real analytic. It does not have a power series expansion. Okay, so let us get into the complex plane. So what is the complex plane? It is ordinary plane, but given some twisted structure, so to say, if you want. C is R2, right? The multiplication is The addition is coordinate wise. The only twist comes in the multiplication, right? So C is a real vector space and also a complex vector space. Of course, real vector space of dimension 2 and complex vector space of dimension 1. So when you talk of a linear map from C to C, you have to specify whether it is R linear or C linear, real linear or complex linear. So what is the difference? Additivity, of course, is the same. Only in the homogeneity, when you pull out scalars, it makes a difference. Real linear pulls out only real scalars, right? Complex linear means it pulls out complex scalars also. So what is the difference between a real linear map from C to C and a complex linear map from C to C? Why do you want to look at this? Because we want to look at what is the difference between real differentiability and complex differentiability. How is real differentiability defined? From R2 to R2, you have looked at several variable calculus, right? Even from Rn to Rm, you have looked at differentiable maps. Okay? Yes or no? So anyway, so we will recall the definition. So when you have a real linear map from C to C, when is it complex linear, for example? So with this usual way of writing complex number, z is x plus iy, but in the element of R2, you write it as x comma y, right? So because you want to look at complex scalar multiplication, right? So what is Iz as an element of R2? I mean, there is no magic here. You look at, right? If you don't want, you don't write it as xy, write it as x plus iy and multiply by I in the usual way. What are you going to get? Ix minus y. I square y is minus y. So the real part now is minus y. The imaginary part is x. So this is minus y x. Of course, you can write down the product of two complex numbers. You take a plus ib and c plus id. So ab into cd is going to be whatever you get, right? By multiplying out. ab minus ad minus bc plus I times something, right? Let us look at t from C to C. R linear. This means T of Z plus W if T of Z plus T of W, and T of alpha Z is alpha times T of Z for any real alpha. Okay. But how does a general map from C to C look like? Real linear map. Forget C now, we look at it as R to R2. How does a general linear map from R2 to R2 look like? T of xy is T is going to be of the form is given by a 2 by 2 matrix ABCD, right? So AB into xy, CD into xy. So you're going to get AX plus BY Right? So this is T of Z. Whenever, unless you are going to write something, you want something of this time, I will write, instead of writing Txy, I will write this Tz. Okay? When is this C linear? You want to multiply by a complex number. So T of alpha Z. You want to, alpha is A plus IB, let us say. So A plus IB times Z is AZ plus I times BZ. You can pull out A or linear. You can also pull out B. Right? You can write it as A times T of Z plus B times T of IZ. I you can't pull out unless you have complex linearity. So, because you already have real linearity, this is going to be complex linear if and only if you can pull out I. Right? T is C linear if and only if T of IZ is I T of Z for all that. Right? So let us write down each side. We already have written down what T of Z is. Okay? So what is I of T? What is T of IZ? T of IZ. What is IZ? Minus y minus x. So this is T of minus y x. This is A times this plus B times that minus AY plus BX minus CY so check, don't copy what I am writing, see whether it is correct or not. Make any corrections if you needed. Is that okay? Fine. So let's see what the other side is. I of Tz is. The I of Tz is this. So what do? You flip and put a negative sign in the first one. So minus Cx minus dy Ax plus by. So when are the two going to be the same? So T is C linear if and only if what? So this is equal to this is equal to this for all xy. So what do you get? The coefficients must agree. C must be equal to minus B and A must be equal to D. Right? So remember this. We will come back to this later. Okay? Of course, any linear map is already R linear, so there's nothing to say about the. So let's now look at differentiability. Suppose omega is open f is a complex valued function on omega. You take a point z0 in omega. So when do you say that f is differentiable? At z0, complex differentiable. Usual definition. This limit exists. Of course, if you want, you can write this as f of z0 plus h plus minus f of z0 divided by h as h tends to 0. Of course, you can rewrite this without writing the limit explicitly. You can rewrite this plus a reminder term. So what is R? Take this to the side. So R should satisfy where R is small compared to Z minus Z0. Was one frequently writes small o that means when you divide by z minus z0 it tends to 0. Small o and big O. Big O means it remains bounded as z tends to z0. Small o means it goes to 0 as z tends to z0. These are convenient symbols, but you don't have to worry about too much. Right? These are called Landau symbols. So R is small o of H. The remainder term, so to say. Now once you have this, you can. The f is a complex valued function, so as you usually look at its real and imaginary parts, if you write f as u plus iv, u and v are functions, real valued functions of z defined on omega. Assuming that this limit exists, suppose f is differentiable at z0, then so that means this limit exists. So whatever way z approaches z0, you are going to end up with the same limit. So we can, for example, look at the approach along the real axis. and approach along the imaginary axis. That means you give the increment only in the real part, real coordinate. So in other words, so take say h real. So look at f of z0 plus h minus f of z0 over h. H is real. So if you write in terms of xy, so you are going to get u of x0 plus h y0 minus u of x0 y0. If you look at only the real part, right? And similarly, we will have for v. So real part of this will be this, and similarly we will have so suppose now is differentiable at z0. So we already are assuming that this limit exists, right? So which means both these limits exist, right? So, but what is the limit of this? This is the partial derivative with respect to x, right? So the limit of this let me write z0 itself, okay? Exists. Similarly, this one and this limit is nothing but this plus I times this, right? F is u plus iv. H is real, remember? So f prime at z0 is ux at z0 plus I times okay, this plus I times this. Instead of writing x0 y0, I am writing z0, okay? The same way you can take a purely imaginary, that is you can come along the imaginary axis. You take IH here and do a similar thing. What will you end up? Similarly, considering IK if you want, z0 plus IK, K in R now, okay, and doing a similar analysis, you will see that you have to divide by IK and that, okay, x0 comma y0 plus k and so on. So, and divide by IK there. So, you will get, tell me what we get. Remember there is an I in the denominator. So what do you get? F prime z0 is this as well as this. So the real parts are equal, the imaginary parts are equal. So you get So these are the Cauchy-Riemann equations. I mean, this is nothing new. This you must have already seen. Let's look at real differentiability. F is real differentiable at Z0. Means what? Of course, this might have seen only for real functions. So let's say define f is real differentiable at Z0 if u and v are both real differentiable at Z0. But what do you mean by saying that u is real differentiable at Z0? So f is real differentiable at Z0 means f of z and f of Z0 are equal to f of Z0 plus where what is this? This is a real derivative, right, of f, which means derivative of u plus I times real derivative of v and so on. So where df Z0 is real linear and R is remainder term as before, and the only difference is here it is real linear, in the complex differentiability it is complex linear. That is just complex linear from C to C is what? What are the linear maps? Complex linear maps from C to C? Just multiplication by some fixed complex number, z going to alpha z, right? For some alpha. These are all the linear maps from C to C, complex linear maps from C to C, right? So there you had f dash z into z minus z naught. The complex case, right? So there's multiplication by f dash z naught. So that is complex linear. Okay, so, but here, of course, we know from real analysis what is the derivative in terms of the Jacobi matrix you can write, right? Of course, this itself you can put into two parts, okay, into the real part and imaginary part. So you can write u of z is equal to u of z naught plus what? So what is the Jacobian matrix? You have f is equal to uv, right? So ux, uy, vx, vy. So you can write it as ux into x minus x naught plus the first row, okay? So you will have something like this. The Jacobian matrix here, it is the x coordinate, y coordinate here, okay? So ux, uy, this is a Jacobian matrix. Here, z minus z naught, okay? So, ux, z minus z naught is, so the x minus x naught, y minus y naught, okay? So, ux into x minus x naught plus uy into y minus y naught. This gives you only the real part, okay? Ux at z naught into x minus x naught plus uy at z naught to x minus y minus y naught plus the remainder term, corresponding remainder term. Similarly for v, vz okay, so this single equation, therefore, is split up into two real equations. Of course, R here will be R1 plus R2. R1 plus IR2. So R1 over Z minus Z naught, R2 over Z minus Z naught, both go to 0 as Z goes to Z naught. So now go back to this. Real linear map is complex linear if and only if the matrix entries satisfy this. Okay? So the matrix here now is the Jacobi matrix. So what is this? So what do you get? Back to Cauchy-Riemann, right? So this is, so and only if what? So what have you proved? The real differentiability will give you complex differentiability provided Cauchy-Riemann equations are satisfied. Conversely, if you start with assuming that f or u and v have first partial derivatives which are continuous, right, then you get real differentiability, right? So in addition, if Cauchy-Riemann equations are also satisfied, you are going to get complex differentiability, right? So you have seen this, right? If u has continuous first partial derivatives, then it is differentiable, and the derivative is given by whatever formula that we have written there. Okay? You just need the mean value theorem to prove that. Simple consequence of the mean value theorem. Okay? So what are the things that we have proved, observed so far? So for a function like that, the following are, do this theorem if you want. F is complex differentiable at z naught F is real differentiable at Z0 and Cauchy-Riemann equations are satisfied. At Z0. Lastly, you have continuous first partial derivatives satisfying the Cauchy-Riemann equations. F has, so I will just say, when I say F has continuous partial derivatives, it means U and V have continuous partial derivatives, okay? F has continuous. This is important. Without continuity assumption on the partial derivatives, the result is not true, right? You don't get differentiability, real differentiability, just by assuming the partial derivatives exist. And CR equations are satisfied. So, what makes all the difference between real differentiability and complex differentiability is what? The satisfaction of the Cauchy-Riemann equations, right?